In this video, I want to look at the question, what is a limit? And I'm going to start with an example. I want you to think of firing a spitball out through a classroom window. So you pull the ruler back here and you have the spitball on the end of the ruler and you fire it through the window. And I want you to imagine there being a speedometer on the spitball. It's kind of ridiculous, but it's just a story, so we can put a speedometer on it. And it's going 3.5 meters per second, then it's going 3.1. It's slowing down because of air resistance. And let's assume that it takes 1 second to get to the window, and as it goes through the open window, it's going 3 meters a second. Now, this being a math video, of course I'm going to start looking at graphs. And this is a graph of the velocity. This is in meters per second. It could be a curve, could be a straight line. It really doesn't matter, but you see at the 1 second mark, it's going 3 meters per second. Now, I want you to think of what happens if we close the window and we do it again. It's going to start out the same way, but when it reaches the window, the closed window, all of a sudden the velocity is 0 because it just sticks to the window. Now, in both cases, the limit or the number we're approaching is this 3. The value in this one is also 3, but the value here is 0 at the 1 second mark. So what you could say is the limit is what we're expecting to get. It's the expectation. Here we achieve that expectation, here we don't. So it's kind of like in life. Sometimes you get what you expect, and sometimes you don't get what you expect. So the limit is what you're expecting to get at that t value, or it could be an x value. So I'm going to look at a mathematical example here. I've got a function that is undefined when x is 5. You see 25 minus 25 is 0, 5 minus 5 is 0. So we do not have a value when x is 5, but we can approach 5. As x gets close to 5, we should be getting some value. So what I've done first of all is look at it in a table. I'm taking x values that get closer and closer to 5. I came down from 6 and I came up from 4. Both times I approached the number 10. This is easy to do on your calculator. All you have to do is plug this x value into here and you'll get this y value. So in both cases we are approaching the value 10. So that's what we call the limit. It's not the value or the answer when we get there, but it's what we're approaching. Now, it's too time consuming to make a table like this every time, so basically what we do is this. Since x makes the top 0, x minus 5 will be a factor. That's the factor theorem. If a number makes this 0, x minus that number will be a factor. This is easy to factor anyway, it's just a difference of squares. And if we divide top and bottom by x minus 5, we've just got this, x plus 5. And as x approaches 5, we get 10, which is what we were approaching in our set of tables up here. If you want to look at this on a diagram or on a graph, the graphs of this line and that function are exactly the same except at one value, the value 5. This is a straight line, slope 1, y-intercept 5. It comes up like this, goes straight through. This is exactly the same thing. This is what I reduced on the previous page, 2x plus 5. The only problem is it doesn't have a value when x is 5. The value is undefined, but the limit is still 10. Here's another example. The examples I'm looking at here involve getting 0 over 0. You see, when I put the 3 in here, I get 9 plus 3 minus 12, which is 0 over 0. So that x minus 3 is guaranteed to be a factor on the top. You eliminate those factors, we simply work with x plus 4, and that tells us that we're getting close to 7. And once again, I've got an illustration here. This is the graph of this function. If you haven't encountered this before, you're probably surprised to see that a function with an x squared in it actually is a straight line. But it is. It's just this line, y equals x plus 4, but there's a hole in it at 3, 7. Now this example is a little bit different. It's not really a polynomial, but it's the same idea as before. If I put a 4 in here, I get a quarter minus a quarter. So I've got 0 on the top, I've got 0 on the bottom. So somehow I have to find a factor that's the same on top and on the bottom. Now, how I'm going to do this is, first of all, I'm going to slide this denominator over here. You could think of invert and multiply if you thought of that over a 1, but it's just sliding it over here. That's just for convenience, so I don't end up with a whole stack of numbers and letters here. Then I got a common denominator here, which is 4x. Numerators are now x minus 4. These aren't exactly the same, but the one is the negative of the other, so if I divide one into the other, I get negative 1. And as x gets close to 4, I get negative 1/16. So this is a procedure we use when we get this problem of 0 over 0 when we put that number in. One last thing before I close here. I'm going back to example 2 again, where we were approaching 3 and we reduced it this way. Sometimes on a test or exam, they'll try to trick you. They'll have you approach a number that is not a problem, and you see 4 is not a problem here. So you're wasting your time trying to factor and reduce it. Whether I put the 4 in right here and get 8 over 1, which is 8, or put the 4 in over here and get 4 plus 4, which is 8, it really doesn't matter. So watch out for cases like that where there isn't a problem. If there's no problem, if this is what we call continuous at that value, then you don't have to do any extra work. You just plug the number in and get your answer.